She has been instrumental in getting this workshop put together, and the current situation in terms of travel and everything else and trying to pull this together was really a feat. And also Gil Herrera, who's going to be speaking momentarily, he provided the necessary high-level push and commitment when it was necessary to pull this through. So again, our thanks to him. So with that, I'd like to invite Gil Herrera. He's going to give an introduction to microsystems and overview of some of the things coming from the technology side.
Let's see, one of the benefits of being a director at Sandia, and I might add, one of the few benefits, is that you do have the opportunity to pretty much ignore what is written on agendas and, you know, kind of talk about what you think is important. Again, Gil Herrera, I'm the director of, in 1700 parlance, we call it 1700. The formal name is Microsystems, Science, Technology, and Components, and most people think of me as the MESA director. Again, I think there is a scheduled tour on Wednesday. We welcome all of you to come out and see the facility and hear more about the technology in depth. So here's what I'm really going to talk about. After a brief welcome, I'm going to explain to you, because I think that somebody in management owes it to you, explains the conference situation and the context, and why you're all hungry. I hear stomachs growling. I was here yesterday morning, and you know, and why it took so long to organize a conference and whatnot, because it certainly wasn't lack of commitment on Murat's part or lack of professionalism and efficiency on Linda's. It all is a political context of what's happening with conferences and budgets, and I think we owe you that explanation, those of you who endured all that and came long distances to come to the conference. Then I'm going to talk a little bit about our microfabrication capabilities, both MESA and CINT. CINT is the Center for Integrated Nanotechnology. I'm going to give a few, a series of examples of the value of the fab outside of making integrated circuits for the nuclear weapons stockpile. And there'll be a few examples that are usually centered on what we call a grand challenge, kind of a big idea, and then how multidisciplinary teams that include both people from Sandia and key external collaborators form. And then I'll talk a little bit about the key role of a flexible fabrication facility where, while we're still yielding, with high yield integrated circuits for the nation, we have it structured such that you have the flexibility to let your imaginations run wild and then try new and different things. Even the introduction of living material into the fab, which I'll cover in one project that's going on now. We're printing peptides using modified lithographic processes that you find in integrated circuits. Then I'm going to end with I know we've heard Moore's Law a number of times yesterday, a few comments about Moore's Law, and then give a warning about mistakes that I've seen us make in the past when we try to think about a new technology area with an old context. And that was actually the subject of a paper that I wrote a couple of years ago, dissecting our MEMS capability at Sandia. So on to the first issue. Let's see, how many of you are not from Sandia who are in the audience now? Okay, thank you for your endurance. Murat first approached me, what was it, last summer? Great idea, want to hold this conference, might be able to attract, and very successful in it as it turns out, leaders in the field. Can I have money? Which is what most staff member conversations with directors usually involve. And so I actually found some money. and which is hard in this environment today. But then the GSA intervened. For those of you who don't know what the GSA is, it's a General Services Administration, the branch of the U.S. government that essentially finds space for government agencies. So if there is a Army recruiter in a shopping mall near you, the GSA probably leased that building. And if there's a federal courthouse in your cities, they probably built it and manage it for the government. And they decided to have a bit of a crazy conference that got recorded on video in the midst of a presidential election. That led to a political firestorm that led to exceptionally restrictive rules for conference attendance, and it's causing a huge backlash within the research community to the extent that even conference organizers at a recent Electrochemical Society conference were not allowed to attend. And so there are a lot of rules in place. I think we have to get approval. Let's see, if we were going to provide food to this conference, it was going to require approval of the Secretary of Energy. And all the paperwork for doing that, was a mess. That led to the final decision for you all to starve. And I believe there is food. And some of us came well prepared. Okay. But so a lot of the decisions that made were not about your comfort at the conference. They were entirely this political algorithm for us to have the conference, because indeed we felt it was more important to get the best researchers around and have them bring in granola or pay inflated hotel prices for food than it was to not have the conference. Unfortunately, a number of other conferences have been canceled. We recently had to cancel something called the HEART Conference, and it's the only venue where government researchers in radiation effects have an opportunity to have classified sessions. It's our hope that sanity will prevail over insanity and we'll get this off track. Then a second parameter hit, and it's a sequestration. Did the Air Force people make it the second day? I think they got their flights canceled this weekend. There's a lot of interest from the Air Force community. The Air Force has a very credible research enterprise and funds a lot of government-sponsored and university-sponsored research. And they were told on Saturday they could not come because of the sequestration. And so, we hope that within the next several months this will be ferreted out. But I did offer you that explanation and want to personally thank you and welcome all of you who endured all the consternation and all the craziness and came here to this very worthy conference. Let me talk a little bit about fabrication at Sandia. Again, I have the privilege of managing, our fab enterprise. Semiconductor manufacturing is something that has its roots in the 1950s and was one of the original research areas. Of course, there weren't semiconductors back then, but it was, vacuum tubes and other electronics. But Sandia has actually had semiconductor foundries since the early 1970s. And we've been delivering semiconductors for mission applications, both for the NNSA, the National Nuclear Security Administration, and NASA and other agencies going back into the 70s. We have a rich legacy of contributions to commercial industry, everything from developing ion implantation, useful for implanting semiconductor devices, which led to CMOS. We developed the first design rule checker. We had a number of key innovations that helped the industry save water in using semiconductors, and industry uses a lot of water. Extreme ultraviolet lithography, which may or may not happen, was an innovation that was funded by Intel at Sandia. And back in December of 1960, and there's a lab notebook that if we get a chance I'll show you tomorrow, a lab notebook entry for the invention of the actual clean room. We're celebrating the 50th anniversary of the patent, and it was pretty neat. So a lot of innovation, which has led the government to decide to invest in Sandia for many years. We're now in our fourth generation of fab, and it's what you see in front of you, the Mesa Silicon Fab. It is by today's standard, a dated process, 350 nanometer rad-hard process technology. There's a lot of reasons why this is a good technology for us dealing with radiation effects We might go a little bit further, but not much further. But then we have a lot of custom technologies that I'll talk about maybe in a bit more detail tomorrow in that fab. And for those of you who are snickering at 350 nanometer, I will remind you that the ASCII read machine based on the Pentium Pro, remember that, Mike? Was a 350 nanometer, roughly 10,000 Pentium Pro chips. And so the very first teraflop computer was based on this process technology. I think we saw an example yesterday of Knight's Corner. I think that's the name they have for the Xenon Pi. And that is one chip that has effectively the same performance. A bit misleading, but that just shows how quickly Moore's Law progresses. So from ASCII read to that chip you saw in the excellent presentation, I think that was first or second, whichever one, they're both excellent, has been 8 technology generations of Moore's Law. 8 generations in 15 years, astounding. So that's our fab. The other fab we have, and whereas our silicon fab, it's relatively large, you know, it's on order of 40,000 square foot of clean room space, and then you multiply that by a factor of 5 for other infrastructure to run a fab. We also have what is arguably the finest 3-5 compound semiconductor research and production fab in the world. It was, you know, whereas the silicon fab was occupied in 1987, the compound fab was occupied in 2007, and with 14 growth platforms, we could make any 3-5 material published. Incredible capability. We also do production in there, and just a real innovation hub for Sandia, rather large complex. We also have the Center for Integrated Nanotechnology. That's in collaboration with Los Alamos and funded by the Basic Energy Sciences part of the Department of Energy. It's a much smaller facility, but it's also not in a technical area, and it is optimized around publication and optimized around inviting the global research community to come in and do nano-inspired research. Again, it is integrated nanotechnology. The notion is scaling up nanotechnology innovation into useful devices. It's one of the 6 DOE-funded facilities for that purpose. A point on MESA that I didn't make is there are also hundreds of light labs that help extract innovation. And in fact, we do a fair amount of biological research, and I'll give a few examples. So let me run through, the last one I wanted to mention. This is something near and dear to a couple of people's in here, Art. I see Bruce Draper and Eric Benedictus, who spent a lot of time working on a facilities proposal. We do have 2 proposals pending for replacement for the silicon fab. The broader proposal is this chip squared. It basically is a new facility that would be a 300 millimeter wafer, 90 nanometer process technology facility that would allow us to have an enduring fab for the future to meet DOE's needs into the future, but also provide a basis for much more research that is much more aligned with where commercial industry now. Trusted rad hard and 90 nanometers. The notion of integration, hybrid integration, allows you to essentially achieve performance at lower levels, the 90 nanometer with a 90 nanometer process technology. As it turns out, 90 nanometer is somewhat of a sweet spot. If you look at the ITRS roadmap going back into the 90s, it actually predicted that 22 nanometer process technology would be running at 0.2 volts. I think, as you all know, it's running at 0.9 volts because when you hit 90 nanometers, you know, the manufacturability issues just did not allow voltage to scale anymore. And quite frankly, it also, when you don't scale voltage, you pretty much don't scale frequency. And so 90 was where you hit 2 gigahertz and you hit 0.9 volts, and it's pretty much stopped since then. And so part of the notion of chips is by chip stacking in a way that allows you to do real work instead of just hanging memory on a processor, you can achieve the equivalent function of lower levels of process technology without having to deal with strange lithography, you know, with FinFETs and the like. And so that's part of it. But another big part of it was computing technologies beyond Moore, so high performance computing beyond CMOS and embedded computing, and also something about trust that I won't talk a lot about here, but people in the national security community worry a lot. So this proposal is out there. What was the final number, Eric? 2.2 billion? I think was a final number on that order. I don't know if that'll ever happen. I kind of doubt it will, but it did give us the credibility to get on the books a $950 million proposal for a facility that'll replace our aging silicon fab that'll either be 8-inch or 12-inch, 200 or 300 millimeter wafers. We'll make that decision based upon the sustainability of 200 millimeters, and we'll also we'll make the decision on process technology, when the facility is closer. So let me give a few technology examples, and I have to what time? About 9? Okay. Again, there's a lot of work at Mesa. I mean, the budget of my center alone is $250 million. We have almost 300 patents, 41 R&D 100 awards. There's a lot of activity, and talking about the size of my center is unfair because most of our work is done in collaborations across Sandia and with external partners. So what I'm going to do now is just talk about a few of these collaborations that are at large scale, very quickly talk about the collaboration, and then show how having a flexible fab, where you have people appropriately inspired and unconstrained, people come up with incredible innovations. The first one I'm going to talk about is a collaboration with Rob Leland's organization and mine and others, also what we call 1100 at Sandia, which is solid state physics offense. They've changed their name that better reflect the notion that they do a lot of work at the nanoscale. But it's an LDRD Grand Challenge. At Sandia, that means that you throw $3 to $5 million at a problem for 3 years. So we're talking about a 10 to 15, in some cases we've gone to $20 million investment, multidisciplinary teams, include collaborators outside of Sandia to solve big problems. And the first one is a LDRD Grand Challenge on extreme scale computing. The notion was that by developing the technology both for horizontal integration and also by helping solve the power problem in high performance computing by integrating photonics technology, that you might have a credible path towards exascale. Again, won't go into a lot of details. This is a pictorial cartoon showing the integration and showing the photonics integration. But you might ask, how are we going to, at 350 nanometers, go to exascale? Well, we're not. But what we can do, I guess, let's see, you used what, 10,000 Pentium Pros to go to teraflop. So yeah, we could do this if you did 10,000 to the third power, which probably won't happen. But you can develop all the process technologies, and one of the more critical ones deals with the silicon photonics technology that we developed. Over the years, we've developed within the fab a relatively large IP portfolio in different silicon photonics modulators and switches and filters and all kinds of other technologies that are back end of the line compatible with CMOS process technology. This is the kind of thing that we could port to other fabs that aren't at 350 nanometers. Now, one innovation that came out of this was a technology that won an R&D 100 award, and it was for the lowest energy optical modulator. And do I have a pointer? Let's see. Okay, a pointer that doesn't show on there. Anyway, so basically what we've demonstrated here, and for those of you who are HPC experts, you know off the back of your hand that it is on the order of a picojoule per bit of energy required for electronic communication, chip to chip, and high performance computing. What we've demonstrated here is at least a 2 order of magnitude reduction in the amount of energy for chip-to-chip communication. If you look at the graph on the right, it's 10 femtojoule per bit demonstrated at 12.5 gigahertz. And on the left, we've done 3.2 femtojoule per bit running at lower voltage. And so if a HPC and server farms spend a third of their energy talking chip to chip, this could effectively reduce that parameter. This is IP that is being commercialized and was a result of a joint effort at Sandia. Really novel process technology. We actually have developed under a DARPA program the quantum Zeno effect program, cutting another 2 orders of magnitude of energy off of this number, but that particular technology is not back-end of the line compatible unless having a rubidium vapor chamber in a semiconductor fab will happen soon. Probably won't. Next two I want to talk about are a couple of grand challenges related to quantum information systems. Actually, I have it in reverse order. The first one was looking at how we could fabricate and measure measurement techniques for silicon quantum bit qubits using double quantum dots. Another one was Aquarius, which is for adiabatic quantum architectures. This is where you actually implant ions into substrates. But part of that led to us developing within the fab, and I could talk about this for years, but one slide on this is the development of a lot of IP block around how you would make ion traps. The traps on the right are for ion mass spectrometry. We've actually trapped ions and used those for IMS. And the traps on the right, and the fact that Dave Wineland just won a Nobel Prize has nothing to do with the fact that I put his image on there because he's one of our collaborators, but we actually developed a number of ion traps for him. It's interesting, if anybody in here remembers the technology Liga, some of our recent traps have been in Liga that we've made for the Wineland Group. This photo was on Science Magazine. Those are traps we fabricated for him. Working with the world, we've developed an ion trap foundry that lets innovators take off with their imagination. This particular trap, and those of you who go on the tour will get to see video of an individual trapped ion, and I'll show you how that works on the tour. But this is capability we have for allowing a trapped ion to turn corners, which is definitely a challenge. That's why you have a structure on the Y-bend that only James Clerk Maxwell fans would love and appreciate, and the design of that required high-performance computing to go through. So again, a lot of IP around how you trap ions and use them for information processing. But we also have done photonics integrated circuits. This particular image of a PIC was able to do a NOT gate at 4 gigabit per second. Very, very high-speed photonic switching. And again, we've done receivers, and again, a whole lot of IP around that. All this in a couple of fabs that are expected in the next 5 years to produce over 100,000 components, for our prime customer. The last example I'm going to talk about from a grand challenge perspective was one we did in IR metamaterials. There's a lot of work in metamaterials at the RF regime that's of great import for antennas, for cell phones, and for Harry Potter cloaks for the military. We decided to take on the IR regime because it was more at our length scales, where you could make very small structures that would perform as IR metamaterials do, manipulate light in ways that look like they violate the laws of physics. They really don't. And an innovation we came up with in the fab was membrane projection lithography, MPL, and this is where we could actually lithographically define 3D structures. This chart explains how we do that. In the case of these structures that are about 1 micron in width, it's done using a rather involved process that has high yield, where we are evaporating material on the sidewall of a etched out structure. What the PI is proposing now with this membrane deposition, you can see the length scale there, is that we could probably go down to 1/4 micron and not only deposit metals, but we could probably also do etch and implantation. And that is a proposal he's coming up with. It'll be an LDRD that is proposed. If you could do that, now you're talking about 3D integration, not through chip stacking, but by depositing semiconducting structures in all 3 dimensions. Really novel concepts. Now, using similar techniques of interference, we've made lithographically defined porous carbon electrodes and microneedles that are used for drug delivery. In fact, the bottom drug delivery also won a R&D 100 award a few years ago. It's kind of interesting. I mentioned we won a large number of those awards. About 40% of the last 5 years, the awards have been in biology-related microsystems. Really fascinating development. But again, if you get people to think out of the box in a fab, you would never think about a structure like this, within a foundry for semiconductors. But you don't have to only do semiconductors in a foundry. You could do all types of things, like the next one, which this is a program, and for those of you in biology, and I know there are a number of you probably heard of these microarrays. You could buy scanners to do microarrays. Oftentimes they're used for genetic research, sometimes cancer research. We have an activity now where we are going to print arrays of 100,000 cells, each with a completely different peptide stack. They're 20-mers, a completely different peptide stack in the array. This basically is how the assembly is done. I won't go into the details of the biology, but those of you who understand those charts will understand this one. So effectively what we're doing are creating stacks of 20 peptides. Arizona State University is our collaborator. They're the ones who developed the IP. We are scaling it. And here's how we're doing it. Basically using conventional lithography tools plus a specialized bio tool that'll hold the peptides. It's like 400 of them is what you need in order to build the 20 peptide stack in a 100K array. And then using conventional lithographic methods, the Trek and a very old lithography tool that we could use for apply to this purpose, we're making these devices. Really novel processing that we're doing in that regard. The last slide I'm going to show is engineered neural circuits. And no, I'm not proposing that we're going to build a brain in the fab. In fact, if you really look at the application of this particular work that we've done, it really is engineered neural circuits that are made to study the effect of chem and bioagents on neurons. And so this is just so you can isolate one neuron. And I'm having to look at notes for this one because I don't really understand. Is Conrad James going to come to the conference? Tomorrow, okay. This is Conrad's work. Is he going to talk about it? Okay, so Conrad's just he is an incredibly great scientist, and he's even a better public servant. So if you ever see his name running for office, vote for him, please. What he's discovered is that you can, if you make structures and if you have a kind of a discontinuous line, and then with the right chemicals in there, it fosters dendrite growth. And if you have a continuous line with the right chemicals, it fosters axon growth. And so you can actually make neural circuits that will follow the paths that you want them to follow. And again, who knows with the right investment and the right imagination and the right people what you can do with this class of technology. Okay, last minute, let me just hit on the ends of Moore's law. We're at least as close to the end of the roadmap as we're at the 90 nanometer mode. I already mentioned the first teraflop was done in 350 technology. But the only parameter that's staying in Moore's law is cost. Okay, the only parameter, because we're having to do, there's so much resistance to changing visible light, quartz and chrome in lithography, which we've been using since the 60s. That we're still on the same basic roadmap, and we are playing incredible games in order to go on that. For lack of time, I won't describe it, but remember that terahertz computer I've been talking about? In order to achieve the lithography for 22 nanometers, there is a terahertz computer that is guiding certain processing parameters that I'll describe tomorrow on the tour if I get time. So you need a terahertz computer in order to solve the equations in real time to do this strange lithography. And so it's time for a new architecture. Yeah, and is it going to be some of the other things I showed at exascale and quantum, whatever? I don't know. But Neuro may be promising for that. But as we go forward, the last message I want to give is we can't be limited by a present conception of computing. And we can't be bound to mimicking the brain because that probably isn't going to be the right answer. that we must learn to exploit the parameters, physics, chemistry, biology, math, of the candidate technology on their terms and not on the terms of what other conventions we have based on our training and experience. And here's a good example of that. And it's, I gave a talk kind of dissecting a lot of the progress and challenges we had in developing our MEMS process technology. And this was the first slide. And it's a picture of the Iron Bridge Gorge in England. And if you look, it's the first iron bridge ever made. And they used the best wood carpentry techniques to make that bridge. 30 years later, they built another one using a small, half of the cast iron. And then, of course, another 30 years later, they came up with another innovation, and that was a suspension bridge, which uses a small fraction of the amount of iron. And this is a good example of, we're going from wood to iron, we're going to build a wood bridge out of iron. And so many times in technology, we end up making those mistakes. This chart is some guy named Murat invented this Neuroprobe, and I'll show you it in action. And while it's going up, let me talk about the probe on the right. And since I don't have a pointer, the motor used to run the first generation probe, which was about 2 millimeters long, Murat, is this big. It's dominated by motor. That's because we stuck to the convention. In fact, what I said in the conference is, why are we using a 19th century or a 21st century technology bound by 19th century requirements? So you see that probe, it's about half the size of this one. It actually is a Neuroprobe. The motor that dominates the device, this is the motor here. It's equivalent in size to this little stay. And that's because instead of being bound by convention, instead of designing a motor that required gears and cams and all this crazy stuff, we went to a thermally actuated motor. Okay? Small fraction, it's a couple of orders of magnitude more powerful, and he was able to make a probe that was twice as long, used in neurological research, I believe not in humans, right, Murat? And there's a lot of advantages to that, and if I get a chance, I'll talk about it tomorrow. I want to get off now. But in summary, pitch for Sandia, since we're the sponsor, we have incredible people and facilities that can make just about anything that anyone could imagine. We have a lot of experience in transitioning research to application. Multidisciplinary, multi-institutional teams do great things, especially when unbound by convention. And believe me, some of the things you're talking about in this conference, if you're bound by convention, you're never going to get there. And the last is emerging technologies are best developed with new concepts that exploit the natural advantages of the technologies. Think about what dominates, in this case, you can heat and cool things very quickly, and so you can use that thermal expansion to power a motor rather than thinking about, I need a cam because that's what they used in the first choo-choo chain. And with that, let me get off the stage. Thank you. You need to be wired.
We'll wire you.
So I'm Brad Imany. I'm gonna be hosting the speakers today, and so we're gonna just probably go straight to Karl-Heinz Meyer right now. One quick note, I guess Murat left these pages on on the tables there. And this is just a workshop idea that we discussed, where we listed a few different brain phenomena. The list is by no means exhaustive. And the question is, since we're kind of moving from neural processes into application space. That's kind of one of the goals of this workshop. If just taking an example here of, say, computation with spikes. There was a discussion yesterday about whether or not spikes are the level to be looking at these things, neural systems. Well, what sort of applications would need spikes? Which sort of applications may not need spikes? And that sort of from an application perspective, what the value is there, and then what the limiting factors are. So if anyone wants to, we encourage people to maybe take some, jot down some ideas here. We'll try to collate them, and tomorrow maybe throw some of the ideas up on in the discussion section. So with that, I'm going to invite Karl-Heinz up here to set up.
ensure that we get good educated students in all these different fields. There is, of course, there are two major national projects, the Blue Brain projects run by Henry Markram in Lausanne in Switzerland, and the Spinnaker project, which will be the subject of another talk this morning. They all, in a way, culminated now in the approval of the Human Brain Project, but if you really look to the past, it is a rather consistent roadmap, which I think now led to a very exciting development. Now, as yesterday we discussed a lot on what is really required to start this kind of activity, I decided to change the title of my talk a little bit, and I called it How to Simulate What We Don't Understand. And so in order to do this, I would like to start with an image from astrophysics. Astrophysics was a subject yesterday. Christoph introduced that, and I love astrophysics a lot because I'm a physicist. And so what you see here are two images of galaxies, and the colors here represent actually a wide spectrum of electromagnetic radiation, ranging from infrared in particular up to the near ultraviolet. And the interesting thing is that these two images look very much the same, but they are fundamentally different in the sense that the right one is the result of an observation, and the left one is the result of a simulation on a rather moderate supercomputer. So what I try to claim here is that simulation is actually a tool, and it's a proven tool to understand the link between microscopic and macroscopic features. What do I mean by that? If you just look at that, you may say, well, okay, you show that if you run a simulation and you put in gravity and a little bit of radiation laws, you get structures that look like galaxies. So that's great. So but what you learn from that, other than that you can recreate these kind of structures on a computer? Well, actually there is some very deep microscopic physics hidden in these simulations. For example, we know that very likely there is dark matter in the universe, but we don't know what it is and we don't know what the property of this dark matter is. So what people do in this simulation, they just mix in a little bit of dark matter and they see that the structure we observe disappears or appears. So they constrain the parameter space for dark matter by doing simulations. And I think this is an excellent example where you can really extract fundamental knowledge from a simulation other than just saying, look, it looks similar, which would be rather boring. And of course, the idea is that you might be able to do the same kind of thing with the brain, which is also a universe made of individual galaxies or point-like objects, more or less point-like objects, which are the neurons. But of course, if you look closer, then these objects are not point-like at all. And of course, they also have the problem that they change rather dramatically with time. But in any case, this is a little universe with an interaction over a distance, as discovered by Ramon y Cajal at the beginning of the last century. And there is another aspect, is that these neurons are actually objects that integrate in space and in time. There is an analog problem here by colors appearing and disappearing, but I'm sure you can fix that. I will go on. And so, of course, the idea is that you play the same game as I have just shown in case of the universe. And these are some numbers which are extracted from Henry Markram's simulation. And the important numbers on this slide you cannot see, because they are green, and the green has temporarily switched off in the transmission of analog signals to the video projector, but I will read them to you. So what Henry is doing, he simulates, for example, a cortical column, and the computer he used to that in the past uses 100,000 watts, 100 kilowatts, whereas the system in nature, consisting of about 10,000 neurons, consumes, which is hard to read here, 3 microwatts. So there is a big factor there, and in a very naive fashion you can scale this up. Of course, there are many mistakes I do by doing this. And the brain I can assume to be 30 watts, and then the simulation with that kind of very naively scaled computer would require 1,000 gigawatts, which is, I have the number for Germany now, the currently installed electrical power of all power stations is 170 gigawatts. That means it's 5 times the power installed in that country. And it's clear that this is not the way to do it. And there's another problem there, is that typically the simulation, of course, runs much, much slower than biology. So if you want to study processes like plasticity and learning, you first of all have to spend an enormous energy, not only power, because energy is power by time, and if you have to run this thing for years, it means the energy consumption would be enormous. And of course, in order to repeat an experiment, you would probably have to work for a few centuries. So clearly, just scaling this up would be a wrong thing. And at that point, I would like to return to physics for a minute. If you look to condensed matter physics, for example, what people look at are complex multi-particle systems of typically 10 to the 23 constituents, which are the atoms, and the typical feature you would like to study is a ferromagnetism. And physics has developed a lot of approaches to understand multi-particle systems. For example, you can do a systematic experimental observation of the collective properties. What is a magnet like? There is magnetization, there are phase transitions depending on temperature and things like that. You can prepare probes to observe some microscopic features. You see this microscopic picture up there where you see the Weiss areas, which gives you some idea on the sort of the interplay between microscopic and macroscopic features. Then, more importantly and more closely to what we are discussing here, you can do model building, theory, and analytical treatment. You can do model building, theory, and numerical treatment. Oh, great, but you can read what I say. And numerical treatment. So that's the classical approach, what physics has been done in the last a couple of decades, but there is another approach to it, and I would like to point to this. You can try to build controlled, reduced size, physical model systems, an approach which I would call synthesis. For example, you can put real spins into a synthetic lattice, for example, an optical lattice, and you can put individual atoms on that. And then you have something which you would call quantum emulators. And there has been a recent paper in Nature by Bloch, Dalibard, and others, and they make a very interesting comment there. They say ultra-cold quantum gases offer a unique setting for quantum simulators of interacting many-body systems. And now the key points are there is a high degree of controllability, there are detection possibilities, and there are extreme parameter ranges that can be looked at. And what you get here is something like an artificial solid. Now that idea, of course, is rather old. You all know that this person here, who has been mentioned several times already in this conference, Feynman, he proposed to build these kind of quantum emulators in order to address these problems here. And it's clear that the quantum emulator may be the only way to systematically study these quantum mechanically interacting multi-body systems, because they cannot be simulated on conventional computers. So actually this projector is a bit weak. This is a much nicer slide if it's on a powerful projector. But what I want to say here is that the traditional approaches, of course, what you want to do is you want to describe reality, and the approaches to reality is to do model building and to develop theories. And the recent addition to physics, or to natural sciences in general, life sciences in particular also, is simulation. And I would claim that there is a fourth approach, which is the synthesis. And now if you look at the same thing for the brain, of course you see that there is the easy thing is that the number of particles is somehow smaller, but there are major differences here. So there are short and also medium and long-term interactions. There is a very high dimensionality arising from the network topology. Most importantly, the nodes, the neurons and the synapses, are active and adaptive, and the system is time dependent. It's far away from thermal equilibrium, and it stores and processes information. And the approach and neuroscience has taken so far is more or less exactly the same as for solid-state physics. You observe collective properties, memory and synchrony, for example. You prepare probes to observe some microscopic features. You do model building theory and analytical treatment. You do model building theory and numerical treatment. But of course, there is also the fourth approach, which is to build reduced size physical model systems, and you all know this is neuromorphic computing. The key arguments for neuromorphic computing have been made many, many, many times, and I don't really have to talk about this. There is the low power argument, there is the fault tolerance argument, there is the no algorithm argument. There is no algorithm in the brain, although it might be describable by an algorithm, but if you have a physical model of the brain, you might be able to live without an algorithm and exploring plasticity, learning, and development, if you can do it. There is the speed argument as compared to conventional computing, and possibly and probably necessarily also scalability. What are the challenges? Why is there no neuromorphic computing out there? It hasn't been a success so far, definitely. And I think the key challenges are the following. There's always the point that we do not know enough about neuroscience, and in order to, how do you handle that kind of problem? These are the red words here, and I think that really calls for flexibility. If you don't know what you do, then you make your parameters flexible so that you can try different. This is a systematic approach, which I like very much. The second is they lack configurability. You have a certain model which you implement in hardware, and it takes you 2 years to do that, and when you are done, then the neuroscientists come and tell you, I don't want that anymore because my model has changed. So that's very bad. And so you have to make these systems very configurable, and that calls for technologies for distributed memory. Integration density, of course, is an issue, not at the moment, I think, but it will come. And so we have to be well prepared to apply nano components, and also very, very importantly, to go to 3D integration. Then there is something which has been used very massively in analog and digital circuit design in conventional electronics, and this is the concept of circuit reuse. So we have to develop the necessary computer-aided tools so that we do not use 2 years to design the next circuit, but maybe we can do it in a couple of months. And then maybe the most important point here is, so far, neuromorphic systems have only been used by the PhD students that built them. And if that PhD student went away, the system was dead and the next one was designed. And so what we really need is a generalized user access with a unified software tool set. That is not software to run the as an algorithm, but it's software to configure and the system and to analyze the results. There is more to this, obviously. We are doing a completely different approach here. In conventional computing, it was based on a very, very solid theory, Boolean algebra, which was then put into circuit by Shannon. Turing introduced programmability, von Neumann the architecture, and Kilby, funny enough, the only one who got a Nobel Prize in this enormous list here, he did the integration. Okay, the brain, of course, does not do these things, and we do not start from a theory, but I think we have to start from computing architectures. So where do we go from here? The knowledge of the brain is incomplete. Everybody accepts that. There is the question, what cell complexity do we need? What are parameter ranges? What are network architectures? And are there missing pieces? What about glia? Is the question we hear every 5 minutes. And of course, there are missing pieces. What does it mean? Do we have to wait forever until things are solved? Definitely not. Instead, what we have to do, and of course we start to do this, and we will do this even more in HPP, we want to build in the known features. We know a lot of things now. And in particular now we want to learn how to build neuromorphic systems. That if somebody comes with missing pieces, we can say, well, no problem, we will put them in because we provided all the tools. We have to make systems configurable, and I will introduce something I call the neural FPGA concept, and we have to make them available for non-expert. I will now switch to one of the projects which has been running now for 2 years and is based on another project, Facets, which was running before. And in a way, it's sort of a miniaturized version of the Human Brain project. It tries to link neurobiological experiments with theoretical models, mathematical analysis and computer simulation, and then come up with special hardware, which in this BrainScales project is what we call a hybrid multi-scale facility. And I will tell you more what that really is. So how do you link modeling to biology? This cartoon shows you what has been done. This is now old. It's almost 4 years old now. So what we did in this project is that we used an input current generated by an electronic input current generator. We fed it into a biological neuron and then looked at the response, a subthreshold and above threshold, or the spike patterns. And then a mathematical neuron model was developed. And you try to tune this model to your biological observation, and then here at this moment you shut off the experimental results and you try to predict what happens. You only look at these things after you have calculated the response, and then you see how well this agrees, and at the end you decide that you have a good model. This has been driven very much by Wolfram Gerstner from the EPFL Lausanne, who has also invented so-called neuron contests, where he comes up with input patterns like that and then asks the participants to predict what comes out. The model that has been derived in the framework of our Facets project is the so-called adaptive exponential integrated fire model. There are others which have of similar nature, like the one of Isakevich here, developed in the US, which just is different in terms of this exponential term here. But the basic idea is that, of course, you describe the membrane trace of a neuron, which has a certain capacitance and which has a conductance. There is one single conductance here, so it's a so-called point-like neuron model. It's a very simple neuron model in that sense, but the new additions which we found are these two terms here. There's an exponential behavior here close to threshold. Of course, this is, in a way, the most important part. This is a sum over up to 15,000 synaptic inputs. And then there is this other differential equation which we put in here, which can describe adaptation and also bursting firing modes. To give you some flavor of how this kind of model works and how well it agrees with competing models, this is one of Wolfram Gerstner's input current streams here. So there's time running here. This is the current. It starts with a very simple step current, and then there is this kind of random fluctuation here. And the red curve is the response of the adaptive exponential integrated fire model. And for comparison, there is Hodgkin-Huxley here, which actually looks very similar. So the next step is to put this into electronics, and you start with a kind of a block diagram where you collect all the features. You want the exponential term, you want the membrane capacitance, you want the adaptation feedback, you want to combine neighboring neurons to form kind of multi-compartment structure. And then you sit down and you do this design of your chip here. These are two neurons which actually have all these features, and in this 180 nanometer technology is 150 by 20 micrometers for two neurons. Then you do what many have done before. The next step is to put it on a chip, okay? And that is nothing special. There are lots of chips like that, and in a way they all have the same kind of architecture. So this is a chip which is half a centimeter by 1 centimeter, and there are some observations you can make here. So you typically are completely dominated by the synapses, because here I will show you more what the synapses are really, but clearly the synapses dominate the area, and the neurons, although they are very, very complex and very fancy circuits like the ones I've just shown before, they actually occupy almost no space. So the synapses are the most important thing, and then all this black area here, which again is very hard to read on this, see on this projector, these are the connections. So chips like that are dominated by synapses and the connections. Now, in order to have the maximum possible integration density, in our project we decided to try something which also has been proposed in other areas, which is wafer scale integration, and we built this system which now on this wafer here, which is an 8-inch wafer, contains 200,000 adaptive exponential integrated fire neurons, 50 million plastic synapses, which each can receive. Don't ask me what this is. It just came back like that. Isn't that amazing? Something happened. There was an iPad in between. How did that happen? Amazing. Okay, I'm shocked. Okay, so each neuron can have up to 16,000 synaptic inputs, so per neuron. And the important thing here, I think, is architecture. I mean, this is really a research device. So we have this wafer here, which contains the neural part, the fault-tolerant part, and there is this big printed circuit board here, which is about 50 by 50 centimeters, and it carries 8 FPGAs. These are really standard, boring, old-fashioned FPGAs. And what they do in this system is they allow us to communicate with the neural system here. For example, to configure the parameters of this neural network, to configure the connectivity of the neural network, to send in spikes or currents through current generators on these boards, but also to read out the activity on the wafer. So this is really a system where you can configure and study a network that is running on this wafer. Of course, a lot of technology had to be developed. If you want to do wafer scale integration, you need some kind of post-processing to really be able to send spikes from here to there. This has been done with the Fraunhofer society in Germany, and also you have to send about 10,000 signals. There are 2 gigabits per second links, and there is power being supplied to the wafer. So all these problems need to be solved. This is a computer drawing of the system, which looks like something you could do in the next 50 years maybe, but this is actually a reality. And again, I apologize, the picture doesn't come through nicely. This is what we have in our lab in Heidelberg here. Hidden behind these cables is the wafer. You see the 4 locations of the FPGA control boards here. And at this moment in the BrainScales project, we have 2 such wafer systems in the commissioning state, and 6 wafers like that will be delivered in 2014. And we start to do experiments now on the system, and I will show you quite a few experiments, which however have still been done on individual chips, not on the wafer system. We only start to do experiments on the wafer system now, and I'm not ready to show these experiments in public. But to show you, give you some parameters on what's there on the wafer, this background here, you see about 400 of these so-called high input count analog neural network chips. We call them HICANs. There are 400 of them. There are the neurons here, which are introduced already, 200,000 instances on the wafer, typically 300 micrometer in length scale, analog floating gate parameter storage. And we also have, for our studies of stochastic computing, we have Poisson noise generators, which can inject noise into the system. The synapses are small, of course, as small as we can make them. There are 50 million of them on the wafer. They have a length scale of typically 10 micrometers. They store information in 4-bit SRAM weights and feature these short-term and long-term plasticity mechanisms, Sodix-Markram type plasticity, and also STTP learning, also with a reward factor received from the outside. The architecture for communication is that there are 2 levels of communication. One on the wafer, you can link any neuron on the wafer to any other neuron on the wafer. Of course, if these links are long distances, you start to waste resources, and so there is an alternative. We can go vertically off the wafer, then ask the FPGA to route the spike back to another location on the wafer, or also to neighboring wafers, and also to a computer cluster where we can do analysis. So to build the system in the Brainscales project, and this is what is running now, starts to run, is in the commissioning phase, is what we call a hybrid multi-scale facility. It's hybrid because it joins a conventional computer cluster with a neuromorphic system. The neuromorphic system includes all the microscopic features, and of course we can read out individual membrane traces, for example, or spikes. But we have this conventional computer which basically serves two purposes. One is it can model parts of the neural system under investigation which are not implemented in the neural system. This is what we call a multi-scale approach. So for example, you can have, I don't know, a retinal type circuit. You can have that described just by a normal software model and then join it with this kind of neuromorphic system. The other purpose of these conventional computers is to calculate observables that biologists see, like local field potentials, MRI pictures, MEG pictures, and others. Now the important thing, it makes no sense to build systems like that and just keep them isolated. You have to expose them to an environment, and for reasons I will explain later, this is a virtual environment. We do not connect it to real robots, but to simulated robots, and we are running closed loop experiments there. On the connectivity, I can skip that. Now there are some interesting aspects, because before I come to the results, I will show you some features of this wafer-based system which are interesting to consider. One is the information flow. Actually, if you look to the information flowing coded in spikes on this wafer, it exceeds something like a terabit per second, 10 terabit per second. And on the wafer it's a terabit per second, and off wafer it's a terabit. On wafer there's a zero missing here. It's 10 terabit per second. So that has to be provided, and the technical tools we use are so-called elastomeric connectors, which provide vertical links where information can be fed into the system and read out of the system. And all this is integrated on this printed circuit board. Now the other thing, of course, you have to deliver to a system like that is the electrical power. And of course power is a key aspect of neuromorphic computing. Now I can tell you that this wafer, which is about 320 square centimeters of active silicon, has to be supplied by a power supply that delivers 500 amperes, okay, which is more than the motor you need to start your car. And if the picture I've shown you before of the wafer system would have been more clear, you could have seen the cables that actually provide that power. There are 5 of them, and they all look like that, okay? And it's 1.8 volts that is delivered with 500 ampere. So is this a low power brain-like system? Well, you actually have to do the math. And this is what I did here. There is one aspect, and I will discuss this later, but I can tell you already now, this system is an accelerated system. It runs at 10,000 times the speed of the biological model. So this is one point to take into account. And of course, the other point to take into account that this is a very large area which is being supplied. So just a very, very simple picture. I have stolen this from a talk by Pollack, an ancient talk, 1999, where he has plotted the power per square centimeter as a function of the minimum IC feature size. Of course, these are conventional microprocessors, okay? And he has shown here very dramatically that the power density increases and increases and increases. He has a nuclear reactor here, a rocket nozzle, and the surface of the sun, which we would try to avoid. But our system actually sits, because it's such a big area, the actually power dissipated on a square centimeter is only 3 watts. So that's not so much. And our node, our process node, sits here. So compared to conventional processors, we are really way down. The fact that we need these thick cables is just because the system is physically so large and has to be supplied with power. Now, a more interesting number is the power or the energy. Let's talk about energy. The energy you really spend for a fundamental neural computation. And what we do on this system, and this is a measured value, we spent about 10 to the minus 10 joule per synaptic transmission. So what I do is I just use the total power in the system and I take into account a typical firing rate for the neurons, and I say all these spikes have to be transmitted through the synaptic links, and then I up is 10 to the minus 10 joule. Biology, interestingly, sits at 10 to the minus 14 joules, 10 femtojoule per synaptic transmission. So that means there is a factor 10,000 gap downwards to biology, which sounds dramatic, but there is another huge upwards gap to the high-performance simulation. And this is summarized on this slide, which shows all the energy numbers for neural computation. So we start down here with biology. I said it's 10 to the minus 14 joule or 10 femtojoule. Henry's simulation, which is a very detailed model, of course, there's very detailed neuron models. On his blue gene, he uses about a joule per synaptic transmission. So there are 14 orders of magnitude here. Of course, you can go to simpler models. You can go to point-like neuron models. These are numbers taken from our friends in Jülich, the research center Jülich in Germany. They are running ADEX-type simulations, and they typically use 10 to the minus 4 joule. So this is very simple models. This is very complex models. But neuromorphic computing sits in a gap here. We are sitting down here at 10 to the minus 10. Spinnaker will be discussed afterwards. So I would claim that this kind of gap will not be easily covered by the further development of supercomputing. So there is typically a 10 million gap to high-performance computing and a factor 10,000 gap to biology. So energy scales are really impressive. Now let's talk about something else, which is time scales, okay? And this is just a cartoon of neuromorphic computing. It's an extremely simple model, no threshold, no firing, no adaptation, all these nice things are not there, but it's a simple Kirchhoff-type equation of this circuit here, which is a capacitor and a battery and a resistor. And what you can do now is to put in numbers from biology and from old-fashioned VLSI, actually. So I look for the voltage swing, for the leakage conductance, and for the capacitance. These are typical numbers I took from this Brett Gerstner paper, and these are numbers I put in myself. And then I calculate G times delta V divided by C, which is volts per second, which tells you how many volts you can ramp up in a second in this circuit, okay? In biology, you can ramp up 1 volt, and in electronics, you can ramp up in 1 second, you can ramp up your voltage by 1 million volts. Okay, of course, nobody can do that because you would blow your chip, but what you do instead is you wait for a shorter time, and that means in 10 to the minus 10 seconds, 10 to the minus 6 seconds, you can ramp up by 1 volt. And that just means that the intrinsic time constant of that circuit is much, much faster than the one of biology. That means if you build a system out of circuits like that, it would run faster than biology, and that's unavoidable. You cannot make it slower because these are the time constants of physics. Now, of course, this is just one little aspect of the circuit. It's just this little toy circuit here. In reality, you build something which is very complex. It has time constants of the neurons. It has time constants of the postsynaptic potential, rise time and fall times. It has time constants which determine the time window for STDP. You have the delays. So if you want to build an accelerated system, you have to make sure that all the many physical time constants in that systems do actually match. And we spent a lot of effort doing that, and we claim that we have a system that actually matches nicely, and our system currently, the one I show you, runs at a factor 10,000 faster than biology. So why would you do that? That's completely useless, no? Because you cannot connect it to a robot. You would never have a robot that moves a factor 10,000 faster than biology. But I would claim there is an interesting application, and to me, this is the key of our work. And it has to do with time scales. If you look to nature, there are 15 orders or 12 orders of magnitude, depending on the way you look at it, in biology. If you look for the detection of causality, pre, minus, post, in STDP learning processes, which are part of our system, you typically work at the micro or milli or sub-millisecond level, 10 to the minus 4 seconds. Plasticity acts at the second level, learning at days, development at years, evolution, which may be interesting to emulate actually at millennia. So if you go to a simulation which is a factor 100 slower, let's say, some simulations are factors of 1,000 slower, then you end up that, for example, if you want to study development, you would have to wait 100 years to get a result. Or if you want to simulate a day, you would have to wait 100 seconds. And of course, you want to repeat your experiments because you don't know what your parameters are. Okay? And so there's no way you can study the dynamics of the system with conventional computers, whereas in an accelerated system, you can do a day in 10 seconds. And of course, that's very interesting. Now, how would you do that if you don't know what the circuits are? And here, I think FPGAs tell us the way we could go. FPGAs, you know, are configurable systems. They are not made of synapses and neurons, but they are made of logic gates and memory cells. But they have the concept that they are freely configurable. You can load parameters and you can put in any connectivity you want. The only reason FPGAs are a success, or one of the very important reasons FPGAs are a success, is not so much the hardware. Of course, you need them. Without FPGAs, you cannot do anything. But if you would only hardware, nobody would know how to use these things. The reason you can use them in any second-year university course is that there is a full development environment of software. You can specify your circuit, you can synthesize it, verify, map and route, verify, load, verify, and use. There's a whole tool set which Xilinx gives you, and it's that easy to use. So even if you do not know what these FPGAs are, what the circuits are made of, you can use them, and you can use them to solve problems. And we try to do the same thing in our system. So we start with biological data or biology, then we have a formal network description, the VHDL of neurocomputation, we developed that, it's called PINE. We do a technology mapping, we do a technology routing, and then we load to the substrate. But very important, somebody yesterday said something very, very important. If you build a hardware system, you need a software model of the hardware system to verify what you do. And this is, of course, you can say, why, if you have both, why do you need the substrate? Of course, timing is the issue here. This thing runs super fast. This takes forever. It's just a verification tool. But it's extremely important that you have that, and we call this the executable system specification. Okay, so this is our VHDL for neural circuits, PINE. It's open source. You can Google it, and you will get a free version which you can use. And the nice thing is you've described your networks in PINE. Then you can run it on all known simulators, on Nest, on PCSim, on Neuron, on Brian, whatever you like. And the interesting thing, if you have it available, you can also upload it to our hardware. It's the same description language. You just describe your network once. Okay? So the typical configuration space for our system is 40 megabytes for a wafer. So these are the parameters if you are interested in the details. So where are those parameters, so the 40 megabytes? They are mostly spent on synapses and connections, of course, and 12% on neuron parameters, which are stored in floating gates, and 1% is other. So what kind of experiments are we doing? This is a rapid prototyping platform, okay? And basically we are running two types of loops. There is what we call a biological loop, and there is a generic loop, okay? If you go through this loop, you run the system on, in the future it will be the HPP Neuromorphic Computing platform. You define your parameters which you get from theory or from whatever. You expose this thing to data or to environment. You compare to experimental biology. You don't like the results. You go back to your model. You update your parameters and you run on this loop. And the goal is to get good agreement with experimental biology. Of course, there is another loop here. Maybe agreement with biology is not all you want. And that may not be the ultimate thing. The ultimate thing will be computational performance. So you can also optimize for computational performance. That is actually a very important slide here. It's a statement by the International Technology Roadmap about the use of uncalibrated and noisy components. This is one of my favorite subjects, but I have no time to discuss this here. Definitely, we have to learn to use low-quality components, and I can tell you we have low-quality components on our systems right now, and for the time being we try to calibrate them to make sure they're all the same with the floating gates, for example. We can store parameters so that they're all the same, but we have to use them uncalibrated, and this is one of my favorite subjects which I'm not going to talk about here. So what are the applications we are doing? So in Brainscales and in the future in HPP we define 4 categories of applications and experiments. The first one is what we call fundamental dynamical properties of isolated circuits. So these are the autistic circuits which do not communicate with the outside world, but these are the simple experiments. So we show that there are effects like synchronization, coincidence detection, stability, order, and chaos. And that is, of course, the first step you do to show that the system is functional at all. Then we want to implement and test fundamental generic concepts and theories which are inspired by biology, but which are not in all detailed biological circuits. Liquid computing is one. Probabilistic inference is a very large activity now in my group, and neural sampling. And this is in particular done together with theorist Wolfgang Maaß from Graz University. Then what probably most people expect we should do, biologically realistic reverse engineered circuits in closed loop, cortical structures, cortical columns, functional units. And finally, and this should be the real cool thing at the end, generic neuromorphic computing outside neuroscience. You can think of building neuromorphic controllers for cars, for example, engine control. Spatial temporal pattern detection in data streams. In particular, accelerated systems are very, very important tools to do this. Causal relations in big data volumes and approximate computing. I show you 6 experiments now, which I have to admit are not carried out on the wafer. It's still in the commissioning phase, but they are carried out in the chip that we use on the wafer. And I go very, very fast because time is running out. So these are just toy experiments sitting in these categories which I defined before. This is one in the autistic category. Okay? It's what you know, it's a synfire chain with feed-forward inhibition. It's an old thing. You have excitatory populations of neurons which are sort of dampened by these inhibitory pools. And what you see is this is time, this is number of neurons, and so there is an activity pattern running through the neuron. This is real hardware. And it shows you that although this is an asynchronous continuous time system, that time references can be automatically generated by these kind of feed-forward structures with inhibition. Inhibition is a key, of course. A very important aspect, this is sort of the opposite. It's not a regular structure, but it's to produce maximum irregularity, asynchronous irregular firing. This is a balanced random network defined by Brunel back in 2000, and why do we want to do this? This is the structure here. So we produce networks where if you look to a single neuron, the interspike interval is Poisson distributed. It's a complete random process. Why would you like to produce randomness? Well, if you want to do stochastic inference computing, you need sources of stochasticity. And our claim now is you can use the network itself rather than stochastic elements. Liquid state machines is a typical thing. You have a so-called liquid, which is just a randomly connected network, and then the readout system, which is a tempotron as proposed by Gütig and Sompolinsky back in 2006. And so we feed certain trains of spikes, sequences of spikes into the system, and then measure how long the system remembers after feeding the system in that this information is still there. And you see that there is a fading memory effect, which you can study with these kind of systems. The winner-take-all circuits I don't have to explain. Probably more interesting is this one here. This is now a reconstructed cortical layer type architecture, layer 2-3, which is an attractor memory. That's the work of Anders Landsner and Lundqvist from Stockholm. They are a member of our consortium. So the typical idea is here that you have so-called mini columns which represent attractors, and these mini columns, they do 2 things. They support their own colleagues here, 3 support 3 by excitatory connections, and they try to kill their enemies by inhibitory connections. It inhibits 1 and 2, but it likes number 3. And then there are some tricks here like inhibitory pools. And if you inject some noise into the system, you see that this system jumps between 3 activity patterns here corresponding to the 3 mini columns. And here we do something very, very interesting. We compare software and hardware. Okay, you see they more or less agree. This is a software model, this is the hardware model running 10,000 times faster. Now, I said already, we have to get away from this software calibration, but for the time being, it's still interesting to do this. Finally, the last example, and this is the one I like most, not so much because great science comes out of it. It will take a while until great science comes out of it, but because it's the first case, to my knowledge, ever, where a complete outsider uses a neuromorphic computing system. This is Michael Schmucker. He sits in Berlin, which viewed from here is not far from Heidelberg, but of course for us, it's a distant city, and so the system is sitting in our lab, and Michael sits in Berlin at the Bernstein lab, and he developed a model for the olfactory system of insects, which is based on several inputs coming through so-called glomeruli, which are then, there's a decorrelation network and an association network. And he uses this network, which he really extracted from biology. He describes it in Pine, in the description language. He uploads it to the hardware, and he runs the experiment, and he gets interesting results. And there are several papers coming out on that. Now, this is the model case for me, how we want to do neuromorphic computing in the future. So this is my conclusion. I think we have a consistent concept. It's done, and that's important. For the time being, it's accessible and available technologies. And my approach is to build something which is big and works, okay, and not to fight the other battle with new technologies. I love technologies, okay. Clearly, we have to learn how to use non-CMOS to integrate this into neuromorphic system, but for the time being, for me, it's important that we demonstrate success. So the key features is universality. This is all the experiments I've shown you are done on the same substrate. This is not a special chip. It's like an FPGA. You upload and you have an insect or a liquid computing device. Scalability, fault tolerance, all that, you know. Accelerated option, I think that is very important. To me, it's the only known approach to bridge all timescales, which are relevant for the dynamics like learning. And of course, this is very essential. We have to give up simulation as a reference, and we have to exploit device mismatch and noise. This is done by this group, which is a wonderful group, about 100 scientists forming the BrainScales collaboration. I probably have, I started a bit later. Actually, I still have, what? There's time left. I could have spoken much slower than, okay. Okay, let me then explain a little bit about the Human Brain Project. So my talk is over. This is sort of an extra now. This is a project, as I said, which many people, I think, have the misconception that this has just been invented by Henry Markram on a Saturday afternoon, and he submitted it to Brussels and got €1 billion. I mean, that is not the case. I mean, first of all, it's based on a huge amount of work over the last decade, all the projects I have shown before. And also, we started to prepare this project about 3 years ago, okay? And there was a pilot phase, a 1-year pilot phase, where we really worked extremely hard to hammer out all the details of the work we want to do. I spent myself half a year in Lausanne working with Henry on the preparation on this project. And this is not just this idea of simulating the brain, and everybody says it's a crazy idea. Of course it's a crazy idea, but there is a lot of detailed thinking behind this. And if you want to know more, there is this report, which is the public report. That's on the web. It's available. You can download it. I mean, that's more sort of the journalist style, but still it gives you some kind of impression. The full proposal, which we submitted in October last year, I can tell you it's a 700-page document where really every bloody detail of the project had to be described. And so it was really hard work to get this done. So the approval of what is a 30-month ramp-up period, so it's not that we get $1 billion on our desk and people say work for a year, for 10 years and come back then. It will not be like that. So there will be a ramp-up phase, which is 30 months, which will, we got the approval in January, which was wonderful for us, of course. It was really a key moment in our lives, and we expect to start in October this year. And just to show you a very boring slide, but to tell you that there is a structure behind this. I mean, this is like, maybe it's a bit, I think also like the Allen Brain Project. This is a coordinated and concerted effort. So we have what we call divisions. And these are the divisions where sort of the scientists from different disciplines work. And this is our work program in a way. So this part here is all the neuroscience, starting from the subcellular neuroscience, going through cellular neuroscience to cognitive neuroscience. Then we have a very strong theory department. So this project will be, although some people claim that's not the case, but it is the case. It's extremely open to theoretical neuroscience. We will found an institute for theoretical neuroscience in a terrible place like the middle of Paris. So if anybody wants to go there, we have fellowships, and so you can come and work with us. Then there is this green block here, okay, and this is what we call the platforms. So really the CERN model is a little bit behind this. We want to provide platforms where people initially from the project, but later also from outside the project, will work with us. And there are 6 platforms which are all technology platforms. So they are brain simulation, they are high-performance computing, there is neuroinformatics, there is the neuromorphic computing platform, which I will describe a bit on the next slide. There is, what else is there? Medical informatics, and of course neurorobotics. The neurorobotics, which is simulated, because timescales of both the simulations and of the neuromorphic systems are not properly matched to the timescale of nature. The simulations run slower, the neuromorphic systems run faster. So you have to work with simulated worlds. But it's extremely important. And the last thing we want to do is to build autistic systems. That's not the goal of the project. Again, this is a misconception which is often spread in the world. So these platforms will be ready, and first versions, that's the plan, will be released in month 30, so it means in the ramp-up phase. And here, these are the applications. Okay, so we have a whole bunch of applications, and I will just show you an example. Now, on the future computing, there are these three platforms, high-performance computing, neuromorphic, and neurorobotics, which are all have their own goals. For example, high-performance computing. The goal is to make supercomputing interactive, which is extremely important, because there is no way you can store the data and then analyze them later. It would make no sense. You would gain all the advantage of running fast simulations. So interactive and visual supercomputing is a very important thing. On neuromorphic computing, the goal is to build what I would claim will be the first large-scale neuromorphic system that is superior in HPC, which means we have to demonstrate that we can solve problems that are not addressable on von Neumann architectures. And neurorobotics definitely is to do with virtual closed-loop experiments, which is extremely important. Let me just give you one concrete example for a workflow to tell you that this is not hot air I'm talking about here. This is a well-defined workflow in HPP towards novel computing architectures, and it links Henry's work with our neuromorphic work. So the goal is that you simulate, reverse engineer detailed cell-based network models in closed-loop virtual robotic environments. This is basically what Henry is doing. If you look to his cortical column simulations, they are very detailed cell models, thousands of compartments, and he really simulates all possible details which he got from his predictive models. And of course, the question is, how can that be useful for neuromorphic systems or for novel computing architectures? Because probably a lot of the details he has in there are not useful. But how can we know? We don't know. We have to find out. That's a research topic. You cannot guess, but you have to address it systematically. And the goal is to calibrate these kind of systems in cognitive performance with experimental data. This is the closed loop experiment. Then we will play the following game. We will reduce the cell complexity in these models and watch how the performance degrades. And of course, the idea is that at some point the performance disappears, and we have to find that kind of sweet spot. And we don't know where it is. Nobody knows that. Okay? And then we would export this to our neuromorphic prototyping platform, which then has the advantage that we can tune parameters on a very fast time scale, and we can study the learning capabilities of the circuits across large time scales, because these simulations will never be able to simulate biological days. But here we can see how well are these circuits able to learn. And then we have a system which hopefully does interesting things. And then the last step would be, because this is a prototyping system, the neuromorphic system I described, and the same way you would probably never put an FPGA in your cell phone for various reasons, but you would then probably export that circuit which you optimized to a special chip. And that is what we want. We have an export facility to go to custom chips, which then we give up the configurability, of course, but then we have specific chip which is originally based on biological input, which hopefully will then be compact, truly compact and low power. So that's the plan. The project will start in October. I recommend that you watch it. I think it will be interesting. And this is interesting. So the iPad mini is appearing again. I didn't touch anything. Okay, so this must mean something. And this is the end of my talk. Thank you. Yes?
About 4 or 5 slides back, you had 4 project goals for what you were going to do.
Yes, I'll find it.
Could you talk about what type of timeframes you think you're getting to these different steps?
Well, actually, these 3 steps are underway today. We do all this. I mean, we have shown synchronization. We are doing experiments on liquid computing, and we start to do cortical structures. For example, the export of Henry's cortical column to our wafer system, which are nicely matched in complexity. This is something we are doing at this very moment, and it's not a part of HPP, but it's a part of the BrainScales project. So this is all running. In the very near future, I hope we will have some really exciting things in this area here, probabilistic inference and neural sampling. And of course in HPP, the important thing is that we go to larger systems here, and the larger systems will be multi-scale, definitely. So we cannot have a full brain to all detail, but maybe that's not necessary. So I would say all this here, this is being done at this moment, and here we started, and we'll go to bigger units successively following the development at the EPFL Lausanne. This is a dream, but maybe not totally unrealistic. We have joint projects, I can tell you, with European companies. That is SAP, which you know is a company very much into data mining. And of course they work with us on this aspect. This is also part of HPP, so I hope we can start soon. This controller thing, of course, I mean, the immediate application you can think of is the automotive area, and here we have a collaboration with Bosch, who may know, they do the ABS braking systems and things like that. You probably would not like to see your braking system rely on a neuromorphic controller, but maybe there are other applications.
What's your plan for data sharing? And in specific, is it possible for us at this point in time to download Henry's cortical model in a mathematically detailed way so that, say, we could write C programs to implement it?
Not at the moment, because at the moment HPP is the Blue Brain project is a Swiss project, and they have their own rules and regulations. I mean, HPP hasn't started. On the HPP, we plan to have an open access strategy.
So at some point in the future, we'll be able to download the cortical model in its full form with complete mathematics and everything?
That's the idea. Even, I mean, what we really want, of course, I mean, that would be sort of our collaboration model, is not that you download the circuit and then use it on your own computer, but that you work with us in the use of these platforms. And it will be a model which is very much like people do it, coming back to astrophysics, in telescopes. So we will offer these platforms to the scientific community, all of them, and then we will have open, what we call competitive calls or open calls. And so people can come up with experiments they want to do, and then there will be a selection board which, based on scientific quality, will grant access to the data and to the platforms. That's also part of the project. Yes?
Are there plans to commercialize just the current neuromorphic system?
No. I mean, this is I really see this as a research device, and there is very little, I don't think anybody would buy these kind of devices, because it's clumsy, it's big, it needs, I mean, now I'm telling you all the bad things, it needs still a lot of engineering support. So if we would sell this, we would sell it together with a bunch of engineers to keep it running. So I mean, our approach is really to make this available. So it will always sit in Heidelberg, and we will let it grow. I mean, we have very concrete plans for the final phase of the HPP project. We will get a new building where we will have a large, we are talking about 100,000 wafers with a lot of new features. From neuroscience, we will go to multi-compartment. We will have very interesting plasticity mechanisms implemented. All this is prepared, but it will always sit in our lab and then can be used from the outside. What we want to commercialize, definitely, is this last step. And I mean, that is, I think, where industry and definitely must have, that's the expert to custom chips. I mean, that's, I guess, if you ever want to make money with neuromorphic or brain-inspired systems, is this last point. Nobody would want to have a 5-rack system, or very few people would want to have that, but everybody would probably want to have a special chip. And that export step, that's where the commercialization starts, I think.
So it seems like one of the obvious ways to exploit the fact that you have this mismatch in timescales between the biological systems and the neuromorphic systems is to do some sort of temporal multiplexing. But then that obviously has implications for the rest of the architecture. So are you thinking along those directions at all?
No, I mean, not us. I think this afternoon, as far as I know, there will be another presentation, and I know that they are considering time multiplexing, so I'll leave it to them. I think the HRL project is very much into this, which is a very valid and very interesting approach.
With that, I think we'll move on to break. We'll